All right, we're going to go ahead and get started. Thank you, everybody, for joining this evening. I want to welcome you to the June General Meeting. And just as a quick reminder, our website has all of our information on it. So we've got the Mount Diablo Astronomical Society.net that will link you to the NASA Night Sky Network. That has all of our contact information on it, the newsletter. Make sure you read that every month. Marnie, thank you so much for putting that together. Just a couple of upcoming events. We've got the Golden State Star Party coming up July 3rd through the 7th. We've got the Society Observing on July 6th and Public Astronomy on July 13th. Yosemite Star Party, July 26th to the 28th, and Rene Gandolfi, our member, is going to give us more information on that as our what's up. And we've also got, all the other events listed online and with other clubs. So make sure you check that out. So without any further ado, I'm going to go ahead and pass this over to Rene.
The question showed is how many people have in Yosemite Star Party? Okay, so all of this is kind of total. How many are planning to go this year? Okay, how many of you are virgins? What? So the Yosemite Star Party is an annual event that our club and clubs throughout California have been invited to the National Park Service. It's did not happen for the last 3 or 4 years because of like having kills the forces fire. Plague and the National Park Service. Fires, if you haven't been following the news over the last couple of years, there was a Ferguson fire, there was a fire up by Elder Powell. One of those fires took out all the services and the road. But meanwhile, the Park Service is planning to do some construction. And we can talk about this and we'll probably experience it. What the National Park Service decided was that there was some big curve on the road getting up there, and they took advantage of the fact that they could be paid, and that's what they've been doing. So I'm curious to see what the road looks like. Because supposedly this is the view we get when we first walk up there, and we set up at the amphitheater at Glacier Point. It's kind of spectacular. We got half on scale place. For those of you that have not been up there, this is a quick overview of how to get there. You're going to take the road to Glacier Point right here. You're going to have to park in the parking lot, but we're going to be set up at the amphitheater. So those of you that have 20-inch telescopes, you have to walk from here to here, but kind of we have a way to get there. A little closer view, what happens is you come in on the road into the parking lot, and there's a dirt road there. Usually there are sidewalks that go up there, they put a way for us so we can drive up that road and park the car at the top of the amphitheater one road. Car gets up there, you load up here, you carry your stuff down, and then you take the car back to the parking lot. At the end of the night, you drive back up there and you reload, get out a dog. Preferably, do that with the parking lot start application. Don't go up the pedestrian trail, but the Park Service will get you and you quick overview of the roads coming in. You're going to end up coming up out of the valley or up from Wona and then take Glacier Point Road. We're camping at 5 Creek. Those of you who don't know, it's 26 and 27. I just looked it up. The Capital coordinates are going to peak right around here, but decidedly about 2 weeks later, we have no planets visible nights out there. Unfortunately, we also have a waxing moon, so the moon's going to rise somewhere around 11:51 the first night, and we will midnight the second night. If you put up the report, you know that our western horizon is crashed because we have to be behind us. The eastern horizon is great, but then we're going to have a moon. Yeah. When you come in, you're coming in Breaking Point Road. You're going to drive into the campsite. You will not have to report to the ranger when you come in. We have our campsite inside this part of the park service. You will get a parking, not a parking test, but you get an entry test that shows the gate come in. We camp at the volunteer campsites down here. We are sharing this year with Lauren, but I don't think they've done it, so I think it would be a good problem. And I'll coordinate that in the next couple of weeks.
We can't hear you.
Okay, what was that?
Yeah. We'll have to, there's Zoom time. I'll try to catch it on the break. Can you guys hear me on this mic okay?
Yeah.
Zoom then, is this mic any better? Okay.
All right. That's good. So, campground is 7,200 feet, so we have a lot of trouble with the glacier crossing the fire. It's about 45-minute drive from Yosemite Valley, so they have to the camp down in the valley. We've got a long.
Your mic is not working.
We're getting mixed signals. I have several people say it's working okay, and a couple saying it isn't. So I'll just have to troubleshoot this at the break. Let's see. Sign language.
When you come in, for those of you that are driving and not coming up by there's gas at Plain Flat. There's gas at Wawona. And then there's gas at El Portal. The gas at El Portal is about $1.50 more than themselves. So it's plan for it. We have to store everything that might be consumed by a bear in the bear boxes at night. That's everything. Otherwise, bears do like to enter your car without permission, and they go fast. The rangers get really annoyed with the stuff on that. So that means to face anything else. Fire pits are available. I assume we're going to go out without fires, but that's my policy. And then your baños, there are no showers. There is, as I understand it, running water. It wasn't a year ago. The emissions but don't expect you to shower with water. And it's probably the only thing the water is very helpful. And I will send out the instructions by email that you can sign up. You please do our CPA Wi-Fi network to install the event. Yes, you're on your. So I am. You're good. And I'll get them out to you and you can contact me. And stuff. Anybody who plans to bring a new under 18 or this special event, beautiful part of the second floor. Hope to see you tomorrow.
Thank you, Renee. All right, we have a quick 10-minute refreshment break. Those in attendance here, and then we will move on to our main speaker. And I'm gonna just hop on the Zoomers and see if we can figure this out. Thank you. Okay, guys, we're gonna get started up again. Yes. Always excellent. All right. Well, thank you. So we're going to move on to our main speaker for the evening. This is the Hubble Space Telescope primary mirror failure. Dr. Alan Agrawal, he is an MDAS member and a local physician, will be speaking this evening. He is a passionate, amateur astronomer, an avid deep sky observer, and has a serious interest in the history of astronomy, the telescope, and optics. So Alan currently serves as the vice president of the Antique Telescope Society and gives talks on the history of the telescope. So if everybody could please welcome Dr. Agrawal.
Very good. Can everybody hear me okay? Okay. Is there a way to turn it up? Or? Yes. Is that better? Yeah. Okay, very good. Thank you, Kevin. So thank you all for coming and having me do this talk. My talk is on the Hubble Space Telescope and primary mirror failure. And I hope you'll find that, as I found, it's one of the most interesting stories about one of the most interesting telescopes. So what we're going to do is we're certainly going to talk about the primary mirror failure, but we want to put everything in context because that makes it more interesting and gives us a better understanding of what's happening. So I'm just going to start by saying that in 2012, I read this book, The Perfect Machine by Ron Florence, and if you haven't had a chance to read it, it is just a wonderful book. And he did an amazing amount of research, and his writing is so excellent. And after I read it, it inspired me in many ways. And one is I was already into astronomy and getting excited about telescopes, but it really got me interested in telescopes, especially big telescopes. It really got me interested in the history of telescopes and astronomy, and about the history of optics, optical glass, and substrates. So what we're going to talk about is, so that was kind of my inspiration to getting excited about learning more about telescopes. What we're going to talk about tonight is, here's a brief outline. So conception and development of space telescopes, and how do we even get the idea to get towards Hubble. Some basics about the telescope. It is a very complicated telescope, even now. The optics of the telescope, which we need to understand before we can understand what went wrong. We'll talk briefly about launch, then kind of the heart of the story, the detection of the problem, which is blurry images, as we all know, the analysis of what happened, and we'll do it in two ways. The first is we'll talk about an optical analysis, and then we'll talk about the human side of the story and what went wrong. And then we'll talk briefly about COSTAR, which is the corrective unit, and then we'll say just very brief words about the servicing missions, and one word maybe or two about the future of the telescope. So let's talk about the conception of a space telescope. And I'm going to start my story here with this boy, or this is going to become a very important person. This is Herman Oberg. He was born in Hermanstadt, Pennsylvania, which is now Sibiu, Romania. And as a young boy, he developed scarlet fever. And at that time, it had a relatively high mortality. This is the pre-antibiotic area. And it was a disease which occurred in epidemic. And that ties into the fact that he was for its recovery sent to Italy. He was sent to Italy, and during his convalescence, he reads this book his mother has given him, Jules Verne's From Earth to the Moon. And this book totally captivates him. And this book is tells the story of the Baltimore Gun Club and its attempt to build a space gun, shoot a projectile with 3 people in it to the moon.
Wait, what are you doing?
And this is Herman over as in later years, and he was so inspired in part by this book to study this topic that he becomes one of the founding fathers of rocketry. And in 1923, he writes a book, The Rocket into Planetary Space, in which he talks about the benefits of a telescope in space. He writes, in ether space, telescopes of any size can be used because the stars do not twinkle. Of benefit also is the black color of the sky. So this was written in 1923. This is the first publication we have suggesting that there should be a telescope in space. And of course, at this time, rocketry is just in its infancy, and these ideas are just dreams. And just for completeness sake, I'll mention 2 of the other people who are considered founding fathers of rocketry. And one is Robert Goddard, and the other is Konstantin Tsiolkovsky. So now we're going to advance by about 20-some years to the American astrophysicist Lyman Spitzer, who writes a paper proposing a large space telescope. And interestingly, this work becomes classified. And what he notes is the advent of the German V2 rocket has made these ideas that he's having about building and sending a large space telescope possibly real. And he's really thinking big and bold. And he's talking in his paper about the advantages of building 5 to 15 meter telescopes and sending them in space. And this is 1946. And here we are in the modern year 2024. We've only recently launched the James Webb Space Telescope, which is 6.5 meters. So he was really, really thinking big. So let's advance another decade, and now we enter the beginning of the space age. In October 1957, the Russians launched Sputnik, and that was followed by soon after, by a U.S. satellite, which is called Explorer 1, which was launched January 31st, 1958, a few months after Sputnik, and it makes a major discovery, the Van Allen radiation belt. There were actually many early satellite probes to the moon, the planets, the telescopes. Many of these missions you guys know very well. These were done in the periods of the 50s and 60s, and these are all kind of ancestors to the Hubble Space Telescope. And they include some very interesting observatories, the orbiting astronomical observatories, AOAs, and the OSOs, which are the solar observatories. So there were 4 orbiting astronomical observatories that NASA launched between 1966 and 1972. 2 were failures and 2 were successes. The 2 failures were OA01 and OAOB, and the 2 successes were the second one, which was observed from 1968 to 1973 and carried 11 ultraviolet telescopes. Remember, we don't get ultraviolet down here on the Earth from the ground because the atmosphere blocks it. And then the last telescope was the most successful. It carried an X-ray detector and an 800 millimeter ultraviolet telescope. So the first observatory that was launched in 1966, it was designed for heavy X-ray gamma ray observations, but it failed due to an overheated battery. The second one was successful with the UV telescope, and it discovers that comets are surrounded by huge halos of hydrogen gas, several 100,000 kilometers across. The third one, named B, was launched November 30th, 1970, and the payload did not separate, meaning the unit carrying the telescope did not separate from the Centaur rocket. And this caused the whole thing to come down. And this was a $98 million failure. And it came down to the fact that one of the $100 explosive bolt didn't fire properly. So keep this in mind. A small piece, every small piece can lead to a catastrophic failure if it doesn't perform well. And we'll kind of see something analogous very soon with Hubble. And then the last one, named OA03, which is called Copernicus, launched August of 1972. It carried an X-ray detector, the UV telescope we talked about, and it was wildly successful. It got high-res spectra of hundreds of stars, made X-ray observations, and discovered long-period pulse on it. This fascinating, almost alien-looking spacecraft was launched by NASA. This is one of their 8 orbiting solar observatories, and they launched these between 1962 and 1975. This one was the first, and it was launched March 7th, 1962. This one, this is kind of random, but I thought the story was so interesting, I had to include it. This is one that the United Kingdom launched called Ariel 1. It was launched April 26, 1962. It collected X-ray energy data from solar flares, and it could have gone on to do more work. It was destroyed from a radiation belt by this U.S. operation called Starfish Prime, where they detonated a 1.4 megaton thermonuclear warhead 250 miles above the Pacific. And then we'll do one other very interesting looking satellite. This is one that was launched by the Russians, 1965, Proton 1, which collects data and studies high energy cosmic particles. So now let's come back to, after that kind of somewhat interesting detour, come back to the development of the Hubble Space Telescope. So in 1966, Linus Spitzer chairs the first meeting of a committee on what's called the Large Space Telescope. The Large Space Telescope, this is going to be renamed the Space Telescope Project, and then ultimately become Hubble. And initially they thought they'd put about a 10-foot or 3-meter telescope into space. 1969, Apollo 11 lands on the moon. 1975, more for budget reasons maybe than other things, and some conveniences, NASA changes the plan slightly for the size of the Space Telescope. It reduces it from 10 feet to 8 feet. 1977, NASA launches Voyager 1 and 2. And then formally 1977, NASA begins the Space Telescope project after a budget is approved, and sets a very ambitious launch year of 1983. Well, by the time 1983 comes around, the Space Telescope is nowhere near to being launched, and it's actually just a major thing in my mind that happens is renamed the Hubble Space Telescope. So progress is being made on the development of the telescope, and we'll talk about some of the things that went into it. But 1986, Challenger explodes, that further postpones the HST launch, and it's not until 1990 that Hubble Space Telescope is launched from Space Shuttle Discovery. So with that background now, let's talk about some of the Space Telescope basics and optics. So the so here's the telescope size. So you can see it here with the solar panels on the side. Obviously the front doors, or the door for the apertures on the upper left. The length of the telescope is about 40 plus feet. It's got a maximum diameter of 14 feet. It weighs 24,000 pounds. It's got 400,000 parts and 26,000 miles of electrical wiring. This is a complex machine. Here is kind of the organizational diagram for the Space Telescope, and you might look at this and say, "Oh wow, this is just looks like a beautifully orchestrated thing." But I think in many ways, nothing could be further from the truth because, you know, there were a lot of tensions, for example, between Marshall and Goddard. Many people don't know this, but the European Space Agency was a 15% partner in the Hubble project, and they many times got treated like an unwanted stepchild. They were responsible for the solar arrays as well as one of the instruments, the faint object camera. Goddard was responsible primarily for the scientific instruments, the rest of the scientific instruments. Herc and Elmer had kind of the core job of designing the optical to the subunits of the primary, the secondary, the whole OTA, and then Lockheed basically was to integrate everything. And then this is very important. They have responsibility also for the systems module design, fabrication, and assembly. And I'll show you what that is, SSM's system support module. And here is a nice diagram showing the system support module. So basically, we can think about the Hubble Space Telescope in three parts. One is the optical tube assembly. The second part are all the scientific instruments. And the third part is what they call the support systems module, which is basically everything else. So that's the solar panels, the reaction wheel, the antennas for communication, computers, all that kind of stuff. So how is the Hubble Space Telescope powered? Its main energy source is the sun. And it gets that solar energy through two 25-foot solar panels that you saw on the sides. It has batteries to store energies. Originally, it had 6 nickel hydrogen batteries with a storage capacity about equal to 20 car batteries. And its power usage is very efficient. It used about 2,100 watts on average. So, and it originally was launched with 8 scientific instruments. So there are 5 that we'll discuss here, and then 3 on the next page. So there are 2 cameras, the wide field planetary camera, often called the width pick, and faint object camera, 2 spectrographs, a faint object and high resolution, and 1 high-speed photometer. So that's 5 instruments, and the other 3 instruments are 3 fine guidance sensors, which are very important. And they kind of have also second sensory system in it away from sensor. So what they do is they lock, so if you're looking at a field of stars and an object in it, they lock onto 2 stars that are in view at the edge of the field. One star is to basically lock the telescope onto the field so that it lock the attitude. And then the second is to prevent any roll around that star. So those are the 2 stars that are needed. And that frees up the 3rd star for astrometry. So I mentioned that, you know, a lot of us, for example, that take images, we have a guide camera. Well, the requirements for the Hubble Space Telescope pointing accuracy are so great that a simple camera would not be sufficient. So each fine guidance sensor actually has a dual axis white light radio purity interferometer. And what that does is that allows you to get down to 2 milli-arc-second point stability, which is just incredible. Here's the optical design of the telescope. The telescope is 10. Both mirrors, the primary and the secondary, are hyperboloids. The primary obviously is concave, the secondary is convex. So when we're looking at optical diagrams, the light almost always comes from the left. And so we can see the light's coming in, it's going to hit the concave primary, bounce back, hit the convex secondary, and then it's going to come through our detector here. Every time you have variables in your optical system, that's desirable because that gives you what's called degrees of freedom. And the 2 degrees of freedom that are given by the mirror conics, meaning the shapes, are used for control. You get to control 1 aberration for each degree of freedom. So you get to control spherical, they use it to control spherical aberration and coma. So the residual errors are field curvature and a small amount of astigmatism. But these are corrected later in the optical path with optics that are built into the scientific instruments. So this is a very important diagram. If you are interested in optics, it's called a spot diagram. And let's just focus for right now on this one that's this column here that says 0 focus shift. So this is the on-axis, meaning what's seen in the center of the detector, and this is kind of what's seen full field near the edge of the detector. So you know that the spot diagram kind of increases in diameter. And so what I want you to imagine is a distant star. Let's say Hubble is looking at one star, and it's in the center of the field. So the stars are so distant that basically all that light that's coming from the star, when it leaves the star, it's going out radially, but when you're far, far, far away, by the time it gets to you, it's basically perfectly palatable. So think about those light rays coming in as pencils of light, and then all going through the optical system, and then each point is the tip of a pencil striking the image plane in focus, and that's what you get. Now, so you might say, well, how come this what you have right here is ideal. You want all that light concentrated in a nice tight spot. That means you're getting a super sharp definition. Well, what about, why is it enlarging here? This is actually not due to any, mostly any aberration you can see. It's slightly oval, we're seeing slight amount of astigmatism, but most of that globe is all field curvatures. That'll be corrected by the instrument optics. So this is really an excellent design, and that's one of the reasons that people like the RC design for imaging, because you get a very sharp field, or you can, with additional optics, get a very sharp image all the way across the field. So let's look at some of the primary optics data. The primary came from Corning for a cost of $1 million. It's made out of ULE, which is ultra low expansion silica glass. You can think of that as like Zerodor, and it's glass that they make it that way, or they can make it that way, and they dope it with titanium oxide, and done in the right way, you get very low expansion with temperature changes, expansion and contraction with temperature changes. It's a sandwich construction, which I'll show you. There are two 2-inch thick base plates that are fused to a 10-inch thick core of glass supports, and that structure is there so that lightweighting the telescope. And at that time, it was remarkable. They got the mirror down to a weight of 1,800 pounds. Now, since then, lightweighting has advanced quite a bit, and I've read, and I haven't talked to a modern optical engineer, but I've read that actually today, if we made the same mirror 2.4 meters, we could probably get it down to 480, 500 pounds. So here is the mirror kind of deconstructed. Okay, so you can see the front plate. This is where the most important part, and then the rest is basically all support. There's a rear plate, there's an inner ring and an outer ring, and then these are the columns that form the core, and this is all fused together. So, you know, and there are two problems that we can read about, even just making this sandwich construction. The first is what happened is that for whatever reason, some of the edge of the core got fused to this outer edge band, and so they had to cut that and clean that up. And then the second, to the horror of people looking at it, they discovered some cracks, and these cracks were small, 1/4 inch in diameter, in the shape of a teacup. So this whole business became known as the teacup affair. And it was near the perimeter, near the edge of the inside of the front face sheet. So basically be on the other side of this. And you might say, well, it's a 1/4 inch. What's the big deal? It's really not going to have a big impact on the optical quality. Well, maybe you guys know, if you've had, especially here in California, it seems to happen not infrequently, a small rock hits your windshield, and then you get a little crack. And what happens over time to that crack? It propagates. So they were very worried, and they spent a long time trying to figure out how to deal with this. And eventually what they did is they decided to drill it out from the top and then put a plug, and that's actually what's done now. Even, you know, the Stewart Mirror Lab with large optics, when they have cracks, generally they don't want them to propagate. They clean them out, and then polish it up and then put a plug in, so that there's no possibility that those cracks expand and cover other parts of the mirror. So as you all know, probably the primary mirror diameter is 2.4 meters. Mirror weight, we said, so about 1,800 pounds. The secondary mirror is 12 inches. Secondary mirror weight is 27 pounds. And look at this, the imaging instruments that are on board with these optics can image from 110 nanometers to 1,100 nanometers, a remarkable range. And particularly important, I mean, the whole range is important, but particularly important is that UV range. There's a lot of important astrophysics occurs there, and we can't get that information from ground telescopes. The focal length of the telescope is 189 feet. Focal ratio of the telescope is at 24. The focal ratio of the primary is at 2.3. The grinding and polishing of the mirror is done on a fixture containing 134 counterweighted titanium levers, and that's to simulate the effect of a gravity-free environment of space. The mirror is exceptionally smooth. The largest bump or valley anywhere is less than 10 nanometers. Considering that it's a 2.4 meter mirror, that's a remarkable achievement. And there are two mirrors that are built. So NASA did decide that, well, maybe something could go wrong with the one that they were going to have made by PerkinElmer. So they got a backup, which never went up. Nothing, it was never used for anything. It was made by Eastman Kodak. And everyone here, I think, knows already that the PerkinElmer mirror was perfectly designed and imperfectly made. But the Eastman Kodak mirror was perfectly designed and perfectly made. Here is a picture of it. It has a remarkable RMS of 0.014, which puts its spell at 99.2%. And it's just sitting in the National Air and Space Museum in DC. So, and we'll talk about why they didn't send that one. I'll say a brief word about later about why they didn't send that one up. So let's come back now to PerkinElmer. So PerkinElmer got the contract from NASA to make the primary mirror. It took them 3 years to grind and polish the glass. And it was done somewhat in a rush because remember I said initially, NASA said, okay, we want to get this thing up and launched very soon. They didn't know that they would have had additional time to work on it. So 3 years to grind and polish the glass, 3 minutes to put on the aluminum coating. Then they coated it also with magnesium chloride to protect the aluminum and enhance UV reflectance. And the finished mirror had 85% reflectance of visible light and 70% in UV. And here, so I showed you schematic before the mirror. Here is the actual mirror. And it, you know, this is I can guarantee this is a pose shot. You know, clean their shirts are. Definitely a pose shot. And then the next one's even funnier. Just look, the guy's got a tie on and a perfectly clean shirt and the shoes. This is a fully staged picture, but it gives you a very nice idea of what the mirror actually looked like. So the mirror, as I said, this is a really sophisticated project, and they had behind the mirror is a magnesium reaction plate with 792 miniature heaters to minimize distortions from uneven solar heating. On top of that, there are 24 actuators built behind the mirror and arranged in 2 concentric rings of 12 each, and they act like pistons, so they can push up on the mirror or bring it down, and they can exert up to 10 pounds of force to make small corrections to the shape of the mirror if needed. So that's the primary. What about the secondary? The secondary was really well made. It's a convex hyperboloid, 12 inches in diameter. It's made of Zerdorf, another very low expansion material. It's got an aluminum coating and mag chloride overcoat, just like the primary. Believe it or not, the surface smoothness is even better than the primary. And it was tested because it's a convex mirror, it requires a special test. So it was tested by something called the Hubble cell test. And it was found to have an RMS of 0.012, which is just incredible, basically perfect. And the secondary sits about 16 feet in front of the primary mirror. Now, this type of telescope, the RC design requires very good spacing. So in order for the telescope to perform optimally, the spacing requirement has to be within 2.5 microns. So how do we achieve that? Well, 2 things. We have to have the structure such that it doesn't expand and contract a lot as it's being heated by the sun or things changing in space. And then also we have to be able to make fine adjustments to the mirror, so for the secondary. So the main spacing is held by a metering truss made of graphite and epoxy. There's no mechanical fasteners on it, and it's wrapped in mylar to help maintain the temperature uniform. So here is a picture. This is obviously the secondary cage, and this is the epoxy graphite truss, and you can see the full structure there of kind of the core of the OTA. The secondary mirror also has actuators, but they're a little bit different than the ones behind the primary. These force actuators can't form the primary mirror. They can, however, tilt the mirror.
We can't hear you anymore.
Try muting.
The optics are mounted in a cylindrical tube which extends 10 feet past the secondary, and I'll do the schematic of that wide, so that, and it has an angle toward the end. That's all very important because we need to control stray light. You may imagine you getting sun or moon or reflection off the Earth. That's really going to decrease your signal to noise ratio as your imaging gets in the way. There are concentric baffles in the tube, which you'll see on the schematic I'm going to show you. And then the whole thing on the interior is covered with this special black dye called Martin Black, a super proprietary high-end coating to make even the micro reflections minimized. And I'll show you what that looks like. Here's a scanning electron micrograph of the Martin Black coating, and this is 10 micrometers long, so we're really zooming in on it. So these all form little light pits. So you're really trying to get almost zero light hitting the detector. And you have, of course, also all the baffling inside. And then you can see the main aluminum baffle with the raised rings inside to help block the light. And now you get a good idea of how far forward that is on the telescope to block stray light that may be coming in. So this is a great photo of the HST at Lockheed about 1 year before launch. It's inside, I don't know if it's still, but at that time it was the world's largest clean room called the VATA, Vertical Assembly Test Room. And the air in that was filtered into place every 90 seconds while maintaining perfectly constant humidity. So finally, after many years of preparation, HST is launched. It's launched April 24th, 1990 from Space Shuttle, and it rides on Space Shuttle Discovery, and it was deployed the next day. And its orbit is about 569. Average orbit altitude is 569 kilometers. It's an incline about 30 degrees to the equator. Takes about an hour and a half to complete one orbit, and it's traveling at a whopping almost 18,000 miles an hour. There are immediately problems after launch, and there's many mechanical problems you could read about, but I'm just going to mention two. One is that the guidance system's electronic memory gets knocked out for up to 10 minutes at a time from going through the Van Allen belt. And the other problem, which has happened with previous satellites, is the solar array shape when warm in the sun and cooled in the dark, making it difficult to lock onto a target for everything. But they were able to sort through these problems. So here we are now. We finally get to first light after they fixed many of the problems. May 20th, 1990. And what target did they choose? They chose the center or some area within open cluster 3532. The most boring possible choice in the universe. Now, how did NASA come to that conclusion? Well, they came to that decision very intentionally because they certainly did not want to take a picture, have it published in the paper, and have some guy sit down for breakfast with a ruler and make some discovery and scoop them. So, and the fascinating thing is this 30, NBC 3532 is 3 degrees away from 8 at 3 now. I mean, can you imagine what a glorious first light photograph they could have had? Well, they didn't know it was going to be blurry, but in theory, that could have been very exciting. So there's actually two photographs here. The top one is from Grandes, from the Las Montañas Observatory, and this bottom one is from Hubble. And so, you know, we got first light, nothing happened at launch, it's up there, a lot of excitement. Yes, the Hubble Space Telescope is working. But now, then people start finding out, well, wait a minute, we're fiddling with this thing, why can't we get a sharp focus? And there was not panic because they're like, okay, we have a defocus error, meaning we're not getting sharp focus for some reason. Or maybe one of the mirrors is tilted and we don't realize it, but it could be the primary or secondary. Or maybe there's a spacing error. I mentioned how critical that spacing error was. So then over time, confusion sets in, then growing concern. This is just like the stage of depression, then denial. And then kind of after really looking carefully at each variable, the horrible realization that the optics do have a major problem. Then now severe depression does set in, and actually there are actually serious concerns by some people in leadership that some of the scientists and other people, you know, they spent a large part of their career working on Hubble. They get a bit worried, well, maybe these people will get suicidal because, you know, this is just tragic beyond words. So, and then, you know, what's the impact of this failure? This is a couple $2 billion project. What's the impact of this failure on NASA? What's the impact on big science as a whole? So once everybody settles down, then NASA finally develops a plan on, hey, okay, we have this problem. How do we use the telescope effectively the way it is? And then how do we plan for repair? And I'm not going to say a lot about it, but I know we have some real imaging experts. So they did come up with a bunch of deconvolution routines and other things, software solutions that did help improve image sharpness, but just know that that does come at the expense of aperture. So it's like we're using a smaller telescope. So it was helpful. And so then now we know that there's something wrong with the optics, but is it because there's a problem with the design? Is there a problem with the primary? Is there a problem with the secondary? Is there a problem of something that they call orbital absorption? Like the mirror was doing okay in gravity, but now it's out in space and you don't have gravity and something flexed or changed differently. And the analysis later on shows clearly that the problem is with the primary and everything else was okay. And what was the problem with the primary? Well, the primary had massive spherical aberration on axis and off axis. There's not really any significant coma, which would point more to an issue with the secondary, tilt in the secondary. The straw ratio is, you know, 0.15. You know, we were hoping for something in the high 90s. It's abysmal. And the RMS, the mean square error, is about half a wave at 550, which is green light. So the mirror is about 4 waves off. So you guys in the know, if you get a really nice mirror, you hope, oh my God, I hope it's the 8th wave, I hope it's the 10th wave. Well, then you've got a really good mirror. This is 40 times worse than that error. Now here's an idea they had. So how about using the actuators on the back of the primary to solve the problem? The problem is that these actuators can't deform the mirror enough to fix the Hubble mirror's primary problem, but it's not a bad idea because this actually happened in a big telescope in Lucia in Chile, the New Technology Telescope, which is a 3.6 meter telescope, and they were able to use the actuators to help with that. So how bad is Hubble's vision? Well, here's the image on the left of M100. You can see how blurry it is. It's quite bad. And then this is taken with the wide field planetary camera when it was launched. And then this isn't CoStar, which is the corrective optics, because what they did is they replaced out the wide field planetary camera with the new one with the corrective optics built in. And this is what we get with the same galaxy with the Lipstick 2 installed after the 90-degree servicing mission. So this is what it should have looked like. This is what this image should have looked like after the first launch, after original launch. So We do find that, take a look at this image, you can see, you'd like to see a nice tight star here. One of the things that's interesting, there's two things that are interesting. One is, here's a ground-based image of the exact same field at 0.6 arc-second resolution. You can see, you can't see very much with the other stars. So, but we are already seeing, even with the spherical aberration, you're seeing a lot more stars in the field. So just by being out in space and not having seeing effect, you're getting a lot better. But then here's the same camera with the optics corrected, and these are all three of these images that are the exact same field. You can see how much more you're picking up here than here. Here's an image of before co-star and after co-star, which is co-star is the corrected optics that we saw that we were talking about. And this co-star correct the aberration of the other three instruments. The cameras and effective filters are separate from the other. So HST at that time was estimated to be a $1.6 billion project, and after the disaster, Roger Angel, who founded the school of Airline, said this is the single largest mistake that's ever been made in optics. So a major deal, a major screw up. Lou Allen, head of JPL, was put in charge of an investigative team. And we're going to talk, as I mentioned at the beginning, and outline about two things. One is the optical analysis, and then we'll do human analysis. So there are three components that we need to understand how this telescope was tested while it was being made. The first is that there's a refractive null, second is a reflective null, and the third is that there's something called an inverse null corrector, and I'll explain how those are all used. And we have also an important measuring rod to talk about made out of invar. So what is a null test? So this is very roughly. It's a test, it's a system of optical elements that you're going to put into a light path to test a mirror and to see if it's made correctly to its desired spherical shape. And what you do is you send the light through the system and the test mirror, and when it comes back, what you want is the test system is well made and the mirror is well made. You're going to get a simple spherical waveline, and you adjust your system so that you're going to get basically straight lines that will interfere with that. Let's leave it at that for now, and we'll talk a little bit more about how the system is done. So basically, you're starting up here with a light source. So I'm going to go through this is the refractive null. There's a refractive null, reflective null, and an inverse null. So the refractive null, light's going to, and there's a detector that's right here also. So the light's going to go through the first lens of the refractive null, the second lens. It's going to hit the mirror under test. It's going to go all the way back through the system, and you're going to take a picture of it. And if you're getting straight lines, your mirror under test is exactly what you want. Here is, so that was the refractive null. This is the reflective null. And they designed a smaller one to test, or a system to test a 1.5 meter mirror first, and it worked perfectly. Then they changed it around so that they could test the HST mirror. And it's a similar concept. It's a little more complicated, not light starting from the top. You're going to hit the lower mirror here, come up to the upper mirror, go down through a field lens, hit the primary mirror. This is the primary mirror of HST, and you're going to go backwards through the whole system until you come back to the top and you take a picture. Now, why don't amateurs use a system like this? Look at the spacing in front. They all 10 nanometers in order to get accurate results, okay? So this has to be really well spaced. Otherwise, it's not going to work well. But it can be done, and it has been done without any problems. Now, the third null corrector I'm going to tell you about is this one. This is the lower portion. This is the inverse null corrector. And so here's the system of optics. This one is actually used not to test the mirror, but to test your reflective null. So you put this under the reflective null, and you're going to start with the light. It's going to go through reflective null, and then you've got it spaced a very specific distance from the reflective null, an exact distance, and then it's going to go through this inverse null corrector and then come all the way back up, and you're going to take a look at your interferogram. Here's a picture of the actual INVAR rod that was used. So INVAR is a measuring rod. So how are we going to space some of these elements? We're going to use this rod. And why are we using INVAR? Well, it's this special nickel iron alloy that, again, it has a very low coefficient of thermal expansion. So you can rely on its length consistently. So let's look at this diagram here. So here is the INVAR rod. This is the reflective null corrector. And the idea is that you put one end, the top of the rod, at the exact focus of the lower mirror. And then this is your rod length. And this rod is basically the spacer now from this point to where you're going to put the field line. So this point is very easy to figure out because it's the exact focus of that lower mirror. You mark that, then you put your rod there, and then you're going to put your field lens at the other end of the rod. And you know this all works because you're using, they don't have one BBC Max, but they're using some optical ray trace software to make sure that all of the desired measurements are correct, at least in design and theory. So here is kind of the heart of the matter and the heart of what went wrong with the testing system for the primary mirror of the HST. So this is, let's just look on the left, block out the right for a second. This is what's supposed to happen. So you're looking from the top, and what's supposed to happen, this is supposed to be a focused cone of light. And what's supposed to, and this thing, and this is the INVAR rod, and this is the curved surface of the INVAR rod, here's the center. And this thing around the top is an end cap, and that's used to properly position the tip of the rod. So what's supposed to happen is you're supposed to look here, bounce the light off the center of the INVAR rod and back, and then that gives you the information you're getting from doing this tells you exactly where this INVAR rod is in space. And instead of bouncing off the top of the INVAR rod, what ended up happening is there was a small piece of tin, like the tiniest little piece, missing from this end cap. And the operator here saw it. See, this is all covered with anti-reflective coating, and this little piece of paint is missing here. So for some reason, this beam got focused on the end cap. And the difference between here and here is 1.3 millimeters. And that 1.3 millimeters is going to make all the difference in the world. And just to be clear, what's going to happen now is you're going to think your rod is 1.3 millimeters too high. You're like, how did this happen? I need to lower this rod because the field lens at the bottom of the rod needs to go down 1.3 millimeters. Well, this, by the way, null corrector was not designed to be adjusted. So, and we'll talk about that. But now here is kind of the picture of the smoking gun. See this little tiny piece of paint that's left? This is the anti-reflective coating, and it's supposed to go all the way down to the very edge of the aperture of this hole. And here's the blow up, and you can see. Here, presumably, is right where my laser is, where the operator bounced his beam off of, instead of going down right in the center. So it's literally like a penny's worth of paint. And so now what ends up happening is so in order to correct this, somebody went to the hardware store. You can imagine it's got 3 washers, flattened them out. They're 1.3 millimeters thick. And so they were able to move that field lens down to presumably what they thought was the correct distance. So now the field lens is now 1.3 millimeters too low below this lower mirror. Remember that 10 nanometer spacing. So what effect does this have on the grinding polishing of the mirror? Well, it has a huge effect. So when you start off, you make a sphere, then you want to get to, you're going to grind more, you're going to get to a paraboloid. And then if you keep grinding properly, you're going to get to the correct hyperboloidal shape. So if they'd stopped right here, they would have had a perfect mirror. And that's what happened with the Eastman Kodak mirror. They made it right down here. What happened in HST, because that washer threw off that testing system, we ground an extra 2 microns off the edge here. And now we've got too much of hyperboloid here. And so this caused too much glass to be removed, which caused 4 waves of error and blurry vision for the whole telescope. So to give you an idea, also another way to give you an idea of how bad the damage was, you know, a lot of times we'll talk about Strel ratio, which is the ratio of kind of the peak intensity of the area disk to the perfect theoretical refraction pattern. Well, there's another very good, and in some ways I think better, spec you can use called encircled energy, and that's actually what HST spec was. And the HST spec in design was to have 70% of the energy from the light on the area fall into a radius of 0.1 arc second. So we're supposed to be right here. So this is on the y-axis is how much energy, and on the x-axis is the radius and arc second. So we're supposed to be, it's coming up here is very tight. We're a very small distance away from the center of axis, and you've got a lot of energy that's right near the center. And what we get is here, you're almost at 0.7 arc second, where you're getting all the energy you want instead of over here. And over here, we should have gotten, if we were here at 0.1 arc second, this is how much energy we're actually getting from the HST, almost none in that radius. So it really is quite bad. Now, let's switch over. We talked about the optical side. Let's talk about some of the human things, the process of grinding and polishing mirror and some of the things that happen. So rough grinding started on the mirror December 1978. May of 1980 is when the 3 washers were added. And then already in May of 1980, the refractive null shows aberration. So why didn't they jump on this? Well, they didn't think that the refractive null was as accurate as the reflective null. And that happens all the time in optics. You can have different test systems, and you have to understand why one system is working better than another. But there's some other problems that pop up. So in August of 1980, the inverse null showed the aberration. So now this is a problem. Remember, your inverse null is here to test your reflective null, and it's telling you, hey, there's a problem with the reflective null. And then again, we go back to the refractive null. At the end of polishing, it shows aberration, but the reflective null shows the mirror exceeds spec. And actually, throughout this whole process, the refractive, the inverse null also shows that there was a spherical aberration. And later during the investigation, it will be found that the inverse null and the refractive null are actually perfectly accurate. May 1981, there's an internal Perkin-Elmer review, and there's a committee memorandum from senior PE scientists saying, hey, we need a sanity check. No action is taken by PE, even though the report goes all the way up to leadership. Every month, the testing, optical testing manager talks to the manufacturing manager and says, hey, we need to what's called certify, we need to test the reflective null and make sure it's okay, nothing ever happened. And now we come to March 1982, and NASA's like, well, we're not, PE's asking for, Perkin-Elmer's asking for more money to do some more testing, and NASA says, no way, we're not going a penny over the 69 million we had promised you. And so PE says, fine, we're done with the mirror and stuff. And that's March 1982. So here, I think we'll skip, this shows how to certify the reflective null, and I can come back to it in Q&A if people want to see how that's done. And if we now get into the human analysis, so we had a problem right from the bidding phase. So Eastman Kodak, who was a competitor, major competitor for Perkin-Elmer on this project for the optics, proposed making 2 main mirrors using 2 sets of different equipment, then swapping the mirrors, testing each one with the other equipment, choosing the better of the mirror, then adding the secondary and testing the entire system. Well, that sounds fantastic. Cost of $100 million. Well, Perkin comes in $31 million less, and they have an excellent track record. And they said, we're just going to use the two reflecting null, no final test with primary and secondary together, but we can do it for a lot less. And this is what NASA. So we have a long list of problems that occurred if we look at this. We have a failure, and we just mentioned of a plan by Perkin and Hummer to test the primary and secondary together. We had cost pressure right from the get-go. We had ongoing time pressure, and this is a major problem, especially with large, complex optical projects. We had a problem of secrecy, so the optics were being built right next to, military optics, and so that limited sometimes what managers and other technical people that coming in could do in terms of getting access to HST and looking at some of the data. There was poor communication, and a lot of this comes from the this is not my opinion, I mean, it is also my opinion, but it comes from the investigative report headed by Lou Allen, and there was a failure to discuss widely the insertion of the washers. There was a failure to discuss properly the discrepancies between the null tests. There was poor oversight, poor quality control. There was very poor, the investigative team found there was very poor documentation. Obviously, there was over-reliance in the single optical test. They failed to certify the null corrector. And then there was unrealistic cost projections by PE in the beginning, and denial of cost overruns by NASA, and maybe the root of all root problems underfunding by Congress. There was overconfidence and maybe some arrogance on the part of PE. Well, prior to that, they had launched a bunch of military satellites with big mirrors, 5 to 8 meter mirrors looking down on the Earth. And if you want to know more about that, that would be Project Eagle. And if you find anything out about that project, please call me and let me know. I may find out very much. It is still considered, I think, a very top secret, or was a top secret project. And there was even some speculation that people in the military didn't want Hubble to succeed. And I have actually been told, I dismissed that idea initially, but I have actually been told by a senior optical engineer who worked on part of Hubble that this isn't as crazy as it sounds. So I left it in. So at the bottom line was there's an abundance, of poor decision making, multiple points of failure, both in the administrative level and on the technical level, and all in the background of constant time and budgetary pressure. And I thought this was interesting, apparently, and I don't have who said this, but one official apparently said at the cost constraint, Perkin Elmer had to lie to get the contract, and NASA had to lie to get the money. So maybe that is the ultimate root of this problem, because there was a problem with the paint flecking up that you really couldn't spot and fix and correct it. And then here's some interesting points that I've added to this talk. So could the HST primary problem have been detected by a simple knife edge test? Well, it was 4 waves off, so the answer is probably yes. So a razor blade and a couple other things may have been able to figure out that there was a problem. Could NASA or PE selected another mirror in place of the defective one to go up? Why didn't they? Really, I think they believed in their mirror, and they felt like the primary was as good or better than spec before it went up. Otherwise, they wouldn't have let it go up. And Eastman Kodak had promised to test their system kind of end-to-end optics. How would they have done that? Well, they would put the whole OTA in a vacuum chamber. They would have had it pointing up, and they would have had a large flat at the top, and they would have easily been able to detect the problem. And I got that right from a very senior optical engineer who worked at Eastman at the time that this was happening. So I'm sure he was correct. In the end, NASA did kind of sue Perkin Elmer for damages, $25 million, which I think in the big picture is peanuts. I would love to read this court case and find out if I can dig out any additional details. We'll see. Let me stop here. Kind of.
So we've got half an hour more.
Oh, very good. Okay, slow down. All right. So let's talk about CoStar then. So CoStar is the corrective optics that were sent up along with the replacement for the width tape. It also is kind of a complicated piece of equipment. It's got 5,300 parts, 6 mirrors to correct 3 instruments. And I'll show you the layout of the mirrors. And we mentioned the width tape 2 to replace it with 1. And what they're going to do is they're going to take the photometer out. I mentioned there were 8 instruments that originally went up, so that was the photometer is going to be taken out, and then the CoStar unit is going to be put in with its corrective mirrors. And the project was given to Ball Aerospace, and the optics for the CoStar instruments were made right here in the Bay Area by Tinsley. So, and what was the central idea for CoStar? Well, there was a brilliant engineer named Jim Crocker. And he's thinking about, okay, we have this problem with Hubble. We want to send out some corrective optics. How is that all going to look like? And he's in the shower, and he's like looking at the shower head, and it's on this European style shower. So it's got a vertical bar. You can move the shower head up and down. You can pivot the shower head, and you can tilt the shower. That is CoStar. So that is basically on the mirrors on that kind of a system. And so that kind of is the story of his inspiration. And so corrective mirrors on arms on a bar could be the correct position. So here's the optical layout. So again, the light is coming in from the left. So this is just a sample. I mentioned that there's 2 mirrors. So this is M1. That's the first mirror the light hits. That's just a simple spherical mirror, and that's going to direct the light down to M2. And M2, this mirror is more complicated. It's a mirror that's going to do it's an aspheric mirror, so it's got to be made to a special shape. And it's going to correct also the spherical aberration. So it's got to correct the fact that we're coming in at this weird angle, and then it's also got to correct the spherical aberration. And these are small mirrors, and then it's going to sheet it out to the inside of the instrument. So, okay, once they design CoStar and build it, it's got to go up. So there's a crew of 7 astronauts that are going to go up on a space shuttle Endeavour, and we're going to put CoStar in. And they did this over 5 long spacewalk days. Here is the lead astronaut. You guys may know him already, Story Musgrave. He led the 1993 Hubble repair mission. I went to a talkie gig once, and boy, this guy's really and he was just kind of talking about some of the things that he had done in his life. And I would say in my life, I mean, the 2 most impressive people I've ever met. One is Story Musgrave, and the other is I already said that. Story's got like 1 billion hours of flying time, 6 space flights. He was in the Marines. He's got look at all these degrees. He's got an MD even. I mean, the guy is like 12 people in one, and all at the highest level. I mean, he's really one of the incredible. So this is a great photo. Now here you can see that this is Catherine Thornton. She's the astronaut. She's just here by flipped in, I guess, at her feet. And here's the CoStar unit. And you know, it's so interesting. I was watching this thing about Hubble, and I had never really thought about it. But you know, when you're doing this kind of work, like you rip your gloves, what happens? You die. You know, you just everything goes out. So this work is very complicated and requires a lot of training, precision, and caution. Here's another great photo from that repair mission. And so how did we do after the repair mission? Well, we did pretty well, because now we went from a business cell of 0.15 that I showed you up to about 0.9 at 500 nanometers. So that's pretty good. It's not a free ride though. Well, one is literally is pretty well, because I don't know how much postcard. I was just reading, I didn't look up carefully, but I think somebody said another $1.5 million for postcard. So it was an expensive project. And then there's an optical cost too. I'm not so worried about that. There's a little light loss, so you're bouncing off 2 mirrors, you lose a little light, so the aperture is a little bit reduced, but we'll take it. It's a very good solution. And then you guys know that there's been a total of 5 servicing missions. So each time they go up, they put better instruments, they replace the gyroscopes, which keep, but especially the initial ones until they were redesigned, kind of failing over time. And then, of course, it gets a boost into higher altitude because of the drag, and that keeps doing Hubble down. I think right now we're at 530 kilometers or something. Once we get below 500, then it gets to be a bit of a problem. So ultimately, though, actually, all the instruments, all the scientists, all the physics missions, they all have the corrective optics built into the scientific instruments. So ultimately, POSTAR mirror, now like the Eastman Kodak mirror, it's sitting in the Smithsonian in DC, and it was removed. Let's see, Service Mission 4 in 2009, and in its place was put the Cosmic Origins spectrograph. So it is. I was just at the Grand Canyon Star Party, and I got to meet the #2 guy in charge of Hubble, and they're fairly confident that Hubble will continue to take photos through the rest of this decade, it's possible into the next. You guys may have seen there was a recent Sky and Tell article, and NASA has kind of opened it up to people who, there are companies that are saying that they can take the Hubble up a higher orbit. They are able to submit proposals. So there are apparently some companies doing that, but we really don't know what's going to happen. So right now we got 2 out of 6 gyroscopes working, I think, but to my surprise, you can even point with just 1 gyroscope, but it reduces the field at which you can, point the telescope, if you can imagine. So this is a list of some of the, Hubble just had so many amazing discoveries. Obviously, those 2, I think you guys know a lot of them already. And this is my last slide. So here's a picture of Edwin Hubble sitting in the secondary cave. And so this is our telescope's namesake. And he's sitting kind of in the perfect machine of his day. And now you kind of heard the story of how the Hubble was transformed for what somebody called a techno-turkey into the perfect machine again. And it's continuing to change our view of the universe we live in. So, thank you all for listening. And I think we
Now bring the microphone a little bit.
You can't mention a good conspiracy these days, not that people be interested. Now, what would be the reason that the military would not want Hubble to succeed, hypothetically?
Well, I mean, now, yeah, that's a fair question. I mean, I can only, not having any military experience myself, I can only speculate. But I think, once Hubble becomes public, a lot of people in the non-military are working on it. A lot of that technology, a lot of that know-how is going to kind of get out. Maybe our countries that we don't want to have the kind of surveillance technology that we have, maybe we don't want that to be spread around so widely. I mean, that would be my simple guess, but yeah. Does that seem reasonable? Yeah.
Oh, I don't know. They sound far-fetched.
My question is, would they consider bringing Hubble back to go around on the space shuttle and putting the Eastern Kodak mirror?
Oh, that's very interesting. I'm going to guess that's technically not possible to bring it back down. But I would have to ask somebody with more experience about, how the space shuttle is settled with, but I don't think bringing something that large back down to the space shuttle would be possible.
For the Eastern Mirror, for the Eastern Mirror was funded just in case they built the other mirror on the ground.
Well, I think it was just, imagine you have all this development going on, and then the mirror is being made. It's not like, let's say you get close to launch, or a few months from launch, and you have a primary that they're like, well, there's a problem, and we can't fix it. So I think NASA was just like, okay, let's have a backup in case we think that the first one has a problem. In this case, they didn't know that it had a problem, otherwise they would have definitely gone to Eastman Mirror. And I've been told actually that just sitting on the shelf there were other modes where, and this is totally, we're not going to find it literature, but I have heard that in theory there might have been other mirrors that could have been used that were just sitting there north of that might have been used. So yeah, I think so. It was made as a backup if a problem was detected with the primary that couldn't be corrected in time for launch. Then NASA might have been out.
So you mentioned the folks that talked about, he said move the Hubble up higher. I thought some people even talked about trying to fix it. Be more than just move it up higher.
When you say, you mean put in more, you mean also add more periscopes?
Yes, or just do something beyond just moving to a higher.
Oh, yeah, that's quite possible. Yeah, that's quite possible. But the impending thing, I mean, the main thing is the altitude thing. Yeah, it's possible that it's other things to do.
I have a related that maybe with the Hubble and the James Space Telescope, the lessons learned and what precautions were taken here.
Oh, well, yeah, that's a great point, and I kind of put that in my intro to the talk that I sent today. So I think one thing that everybody realized about building large telescopes, especially space telescopes, is that this could never happen again. And so there is a lot of redundancy built into the system now. And so they definitely don't rely on just, for example, one set of optics to test any mirror that can be set in space. But I think there's probably also reorganization, better oversight, more technical people at a very high level who get a lot more information. So I'm sure over the years, a large number of things went into place that made James Webb, as well as all the other telescopes since more successful. Yeah.
This nuclear threat is a challenging accident. And I guess I'm surprised that we wasn't the atmosphere and NASA to foster the same themes. And that's really the most unique and then now. I believe that's much more culturally integrated into NASA to have the sending themes and whistleblowers with our et cetera. So did the investigation mention why somebody from this Perkins didn't bring that forward and get listened to this situation?
Yeah, let me say two things. So when I was at this Star Party and I was talking to the two guys, I kind of just gently asked him, about, I just kind of framed it in terms of NASA's organization and everything. And he really felt like there was no problem back then. And so I think he just, because he's the public face, and so he's not, whatever his private dealings, he's not really able to say it. But I will tell you, I think if I remember reading correctly, what Lou Allen said was that Perkin Elmer and NASA were both at 100% fault. So, he really felt that it wasn't just TV, it was also NASA, and they did not have proper oversight of the project. They didn't get access to the proper documents. They were just unaware of any of the problems that they should have also taken out reading curriculum and stuff. So yeah, I can agree with everything.
Any other questions? Okay, any questions from on Zoom? All right. Thank you, guys. Thank you so much. Wonderful talk.
Hello, you're the president,
Yes, I'm Tara. How are you?
Tara.